So we will. So Siddhabra had told me that the audience is quite varied. So we'll go slowly and we'll cover some essential parts. But if something is not clear, please stop and ask. Okay. So what are phase transitions? Now, if you look around you, you're breathing air. There's air here. You just had some liquid. You're sitting on a solid. Then, some things conduct, some things don't conduct. Insulators, magnetic. So there are multiple phases material around you can be in. Okay. So for example, water can exist water, ice, steam, or a magnet can be sometimes magnetic, and if you heat it up too much, it loses its magnetic property. Now, so therefore, but if it is water, let's say water 30 degrees centigrade and I increase temperature slightly, all properties will change a little bit. Density will decrease slightly, maybe the compressibility will change slightly. But if I change temperature from across 0 degrees or across 100 degrees, suddenly the properties change. So for example, if I freeze water, then it goes from flowing to not flowing. So, so these points where the properties change abruptly, we'll call as phase transitions, and you have all seen even in a kitchen many times. Okay. So the study of phase transitions where things change abruptly has been a central theme of StatMech for a long time, one aspect of StatMech. This is what we will focus on. So one slide on what is the role of statistical mechanics. This was discussed in detail by Siddhabra and little bit by Sashidevan, but let me just give the same statements one more time. So the role of StatMech is not to tell you how something behaves, what are the interactions. That is not its role. But suppose I give you some micro particles and its interactions. Then the role of StatMech is to say, if I go from that micro scale to a scale much larger than that. So in the example of gas, molecules interact. Then I go to size of meter, where the molecules are infinity, a large in number. Then I ask at that scale, what is the property? So the StatMech tells you how to go from this micro scale to macro scale, how to do this calculation. So gas of particles is one example, a standard example. From biology, molecules, protein, DNA, cells, tissues, organs. So at the molecules level, you don't even see what a human being is, but by the time organs come, you have you have something called a human. That property of human was not there before. Or if you put a lot of people together, you have a society. When you have a society, you have a new concept called culture. Okay. So at the level of people, individual people, culture may not be there, but when you put society together, some cooperative property comes at all the scales. When you go from molecules to macro scale, you get pressure, temperature, and so on. So, okay. So understanding the interactions at the micro scale is not enough. You need to understand the cooperative behavior of things put together. Just stressing that it is important to study complex behavior arising from interactions of multiple constituents. Now, what will I try to do in these lectures? So, I'll introduce spin models as prototypical models for studying phase transitions. Later, they will have their own importance as models for different phenomena being modeled. But I will try to focus on them not on being models for any particular system, but as prototypical models for spin models. Then I will discuss how to study them. So I will focus on mean field theories, which are the easiest thing to do. How to understand phase transitions are coming from this analysis, critical behavior, and then I would like to focus, because a lot of modern thing is to understand these things numerically. So what are the numerical methods to understand these models? They will be more general than just these specific models. So mostly how to simulate Markov models and the concept of detailed balance. And with these numerical tools, if I see a phase transition, how can I analyze them and quantify them? Okay, that is the plan. So, there are some people who are not from physics background and so on. So, for them these topics may look intimidating, but I put this quote from Weinberg saying that nobody knows everything. In fact, when you do research, if one goes over the puts into the head that no one knows everything and you don't have to, then the shame of not knowing goes away, and then you are liberated from this fact. It's very difficult, but that liberation makes you, when you see new things, you just pick them up along the way as you need. Okay, so this is Weinberg's first golden rule. So, people who are not unfamiliar, they need not be nervous about it. Everybody has different level of knowledge in one field or the other. It is how you pick up other things that is important. Okay, so let us start with the phase diagram of water. So, water we know can exist as ice, liquid, water or gas. And so, so when I talk about the macroscopic variables for describing a system like water, there is pressure, temperature. What is the ideal gas law? PV equals to nRT. So, N is like rho, density. So, there are only three variables there: pressure, temperature and density. And then there is an equation of state which connects the three. So, there are only two variables remaining. So, that is, I can choose pressure and temperature, or let us say pressure and density, or any combination of any combination of two variables out of these three. So, here I have plotted P versus T, and when I increase temperature, intuitively if I take ice, increase temperature, I become water. If I increase temperature even further, I boil water. So, this part looks correct. If I take gas at a certain temperature, I take gas, then I put pressure more and more, I become liquid. I would expect that if I put more and more pressure, I become solid, but in this case that does not happen. For a regular fluid that happens. For water, somehow this line goes to the left and not to the right. Otherwise, I could have solidified liquid by putting pressure. Okay. So, now a few things to note. So, the solid liquid line goes on forever. So, if I have to go from solid to liquid, I must undergo a line here which I will call a phase transition line. But if I want to go from liquid to gas, there is a phase transition line here, but not here. Okay. So, it terminates some point which I will call C. Now, let us spend a little bit of time in understanding. So, what does it mean that there is a line here from here to here, that there is an abrupt change, but I could have gone like this and come like that, and there would be no abrupt change at all. Okay. So, this point that I can go continuously from gas to liquid without any unexpected behavior means that there is not something different between liquid and gas. They are the same things. However, if I were to go across this line, density will change abruptly. Okay. Now, what happens? So, suppose I was sitting on this point here, what would I see? So, I have expanded this plot into a different phase diagram of T versus rho. So, so there is a liquid gas phase transition here. Now, if I were to plot temperature versus rho, this particular line becomes this whole portion here. Along this line, there is liquid and gas existing simultaneously. Okay. So, this line I will call as coexistence line, where there is some concentration of gas, some concentration of liquid. I do not know what they are, but when I expand it in the T rho plane, I know that I could have been here. This point also corresponds to here. This point also corresponds to here, but the ratio of liquid and gas changes. Okay. So, the coexistence line points, when I see phase diagrams, the coexistence line becomes single line in some variable and becomes expanded in other variables. So, sometimes when you see phase diagrams, do not get bothered that sometimes you will see this range here where there is phase separation, and here they call it coexistence. Coexistence means they exist together. phase separation just means a liquid goes here and solid goes here, and the ratio changes to match what you tell is a density. Okay. And why is that? It says that when you go from here to here, density jumps. So when I go from here to here, density jumps. So when I am here, there are some densities I cannot access. But if I forcibly say that density should be there, then it has to be a mixture of solid and liquid. Now, so that goes there, and that goes here. Okay. Now let me change and tell about the phase diagram of a magnet. So a magnet, a magnet has two variables, which is the temperature of the system and the magnetic field you apply. And let me say this is the phase diagram that you see. So if I didn't have any magnetic field, external magnetic field, and had very low temperatures, then the system behaves like a magnet. So that I will call as ferromagnet. And as you increase temperature, beyond a critical temperature, it loses its magnetic properties, and we will call it paramagnet. So there is some transition here, and there is a blue line, red. Now I can replot it in a different variable, which is, so I can ask what is my magnetization here, because so to understand that, just like I expanded in the rho t plane, I can expand the phase diagram in the magnetization temperature plane, and then above Tc, magnetization is below Tc, there is a point. So if I am here, that can correspond to magnetization from minus something to plus something. I can choose it depending on my ratio of ferromagnetic and of the plus kind and the minus kind combination. Okay. So our aim would be to understand these two phase diagrams in some crude manner. That will be the aim of today's talk. So one of the ways of attacking such problems has to be to look at simple models where the interactions are just enough to capture the phenomena. Okay. Why those are important, we will summarize in the end of the lecture. So there is some very well known model called Ising model, which I will define. Let us forget about the motivation. We will just define a model with on a lattice. So this is a square lattice. On each side there is some variable which is s, and can take two values, plus or minus 1. It can be up or down. Now and then, so I have shown them with blue or red. Now for each configuration you want to assign some energy or Hamiltonian, which says that I do not want this spin to interact with the spin far away. I have just nearest neighbor spin. So for example, this spin interacts with only these 4 neighbors, and the interaction is just SI/SJ. Okay. What does it mean? If 2 spins align, if J is positive, energy is lower. So the energy of a spin of a system where spins are all aligned is the lowest. Okay. If they are all aligned either downwards or upwards, energy is minimized. In addition, you could have a magnetic field which couples to the spin at a site. Okay. So this Hamiltonian is known as the Ising Hamiltonian. Is that clear? It is a spin system plus or 2 variable. The spins can take 2 values and nearest neighbor interaction. And the point is that if J is positive, energy is lowered by spins aligning. Now what is the role of H? If H was not there, I could have taken each spin and flipped to minus spin, and my Hamiltonian wouldn't have changed, because 2 minuses make it plus. But when H is there, it breaks the symmetry between plus and minus. If H is positive, it prefers the energy wise, it prefers positive spins, and if H is negative, it prefers negative spins. Okay. Now when you specify such a model, you must also specify what are the boundary conditions. It can be open or it could be periodic. So often when you define such models, you work with periodic boundary conditions, which means that this spin interacts with this spin and the spin here. So it is like I wrap it around the torus. Why do you do periodic boundary conditions? When you do, theoretically at least, when you do periodic boundary conditions, then you restore translation symmetry. There are no more edges. So, when you do a finite size system, there are two issues. One is the system is finite. Second is there are edges. You cannot eliminate the finite size, but you can eliminate the edges by putting periodic boundary conditions. Okay. So, that is why often when you do on a computer or something, you do with periodic boundary conditions. Okay. Now, that was for the ferromagnetic phase transition. So, that Ising model we are going to study as a simple model for understanding the magnetic system. What about the liquid gas system? Okay. So, now are things okay? Am I going too fast or too slow? It's okay, no? Okay. Now, let me change to ask about how do we understand the liquid gas phase transition. So, you know that there are molecules or atoms going around and they have some interaction with each other. You can take a generic interaction. So, generically when these particles come nearby, they repel. When they go far away, they don't interact, and when they are nearby, there is some attraction. This is a generic interparticle potential. One common example is what is called a Lennard-Jones system, which is what I have plotted here. It goes to infinity at close to when r equal to 0. It has a minima at some point 2 to the power 1 by 6 or something, and then it goes to 0. Now, we would like to make some approximation to this model, to this potential. Oops, all this was stored in the So, this potential looks very complicated. So, let us make it simpler by saying I will put it infinity at some point. I will make a small well here and put it back to 0 here. Okay. Now, so the interaction has now looks much simpler. Then I will say I am going to also disallow particles moving everywhere. They have to live on a lattice, like the Ising model. They have to live on a lattice. So, this is a square lattice, and wherever the particles are there, I have put by a red circle, and the empty sides I have put by a black one or blue. Okay. So, there are some sides occupied, some sides not occupied. Now, if I have a potential like this, it says that one side cannot be occupied by more than one particle, because otherwise they will repel. Okay. It also says that if two particles are nearby, they have a lowering of energy minus epsilon. So, I can write some Hamiltonian or energy for this. Oops, this is I am sorry. So, I am going to write some energy for such a configuration. It says let tau I be 0 or 1. If it is 1, there is a particle. If it is 0, there is no particle. And when two particles are nearby, there is a lowering of energy of minus epsilon. So, I will put the Hamiltonian as minus epsilon tau I tau j. When both are 1, energy is decreased, and in addition I could have the red particles need not be conserved. So, I will put some chemical potential minus mu times tau I. Okay. So, this is a Hamiltonian for a simple lattice gas model, which I motivated from the generic potential. Now, if I change variable, so it is okay, this is my Hamiltonian. Now, I change variables, I say I take a tau I and I write a new variable sigma I, which is 2 tau I minus 1. So, when tau I is 1, sigma I is 1, when tau I is 0, sigma I is minus 1. So, the red particle becomes plus 1 and the blue particle becomes empty side becomes minus 1. So, then all I have to do is to rewrite the Hamiltonian. I have to write the tau I in terms of sigma I, and I will get a new Hamiltonian in terms of sigma I. The second term. Second term is this problem I will consider in a way where the number of particles is not conserved in the grand canonical ensemble. So, whenever there's some work done to put a particle inside. So, mu is like the work done to put a particle inside, work done. So, that is usually called the chemical potential. So, if the number of particles were conserved, that term wouldn't matter, but if I allow particles to evaporate and deposit, then this term matters. Okay. So, now I am going to change variables and I substitute back here, and so this is just simple algebra. Wherever tau I came, I put 1 plus sigma I by 2, 1 plus sigma j by 2, and then I just simplify. When I simplify, I get one term which is sigma I sigma j, a term proportional to sigma j, and some constant. Now, we all know that energy is defined up to some additive constant. So, these constants are not important, and what we are left with is Ising type Hamiltonian, where this epsilon is related to j, which was the coupling constant for the Ising model, where this chemical potential is related to the magnetic field, and the variables are SI equal to plus minus 1. So, the binary gas model, not binary, the lattice gas model is exactly an Ising model. So, if we were to understand the Ising model transition, we should be able to understand the liquid gas transition. Okay. So, that is the claim. In what way we understand? We have to make the statement clear, but it seems that the two models are the same. Ising model is same as a model for gas molecules. Okay. Now, given there is some energy given, but in general in StatMech some Hamiltonian is given. It need not be this, it could be a complicated expression. So, there is a mechanism of how to calculate density, for example, if I give you the energy of a certain configuration. So, there is a recipe. What is the recipe? The recipe says you have to give me what are the possible configurations, what are energy for each configuration. That is part of the model definition. But once I give you that, I tell you that all configurations do not come with the same probability, they come with different probability. If I knew those probability, my problem is done, but that probability is given. That probability, it says the probability of a certain configuration being the correct configuration at a certain time is proportional to e to the power minus e, beta is 1 by temperature. So, if I look at a certain temperature, the probability is proportional to e to the power minus beta energy of that configuration scaled by temperature. Okay. So, but once I know probability of a configuration, I can ask, if I take density for example, my usual definitions of how to compute, this is the expectation value of any observable. Given the probability, I sum over all configurations with the value of the observable for each configuration with the weighted by the probability. So, there is a well defined, this is for equilibrium statistical mechanics, there is a well defined recipe for doing the calculations. So, there is nothing unknown for how to do. The only problem is that if I give you a certain, this is impossible to compute most of the time. The Hamiltonian can be complicated, almost always you cannot calculate. So, either you have to do some approximate techniques or you have to do numerical way of solving. So, there are different ways of analyze. One is you solve exactly. Now, that is one which is very unlikely. Other is to do expansions about known limits. The easy one is to do mean field theory. So, there are multiple ways of doing mean field theory. We will do specifically for the Ising model what is commonly called the Curie-Weiss. I may do Bethe lattice and variation, or at least tell how to do them on different methods. Then the other thing is simulations and otherwise. So, earlier lot of time was spent trying to solve exactly these models because there were no computers available. Then now also some people try because it suits their temperament, but generically there is not much value, it is a lot of effort for little result. Low temperature expansion, high temperature. Previous slide.
What is beta?
Beta is 1 by temperature. Beta is always stands for 1 by temperature, 1 by K times Boltzmann constant times temperature. So in fact, there's a book by Ma on StatMech. In fact, he writes in the future, all that people will require is mean field theory and computer simulations, because mean field theory gives you a nice intuitive feeling of what will happen. Simulations give you a nice quantitative values for each one. Okay. Exact solutions have their value, but is not necessary that everybody should do. Okay. So these red things are what we will focus on in the lectures. Okay. So let me start with symmetries. There's nothing complicated about symmetries. So Ising model Hamiltonian is this. Now suppose I put magnetic field to 0. External magnetic field is 0. So I have a term minus j si s j. Now if I take all the spins and invert it, s to minus s, my Hamiltonian doesn't change. No? Minus j si s j, 2 minuses make it plus. So the Hamiltonian is the same for the spin system for a given configuration as well as all the spins flipped upside down. Now if I look at expectation value of m, then it is sum over, if a spin that all point up is same as the probability of all pointing down, then expectation value of m, the magnetization, which is the expectation value of spin, has to be 0. Otherwise up and down is not the same, but we have magnets with non-zero magnetization. So is it possible to have a phase where the expectation value of spin is not 0, even though this symmetry exists? If such a phase exists, it will break the symmetry, this symmetry. Okay. So I am saying that we explicitly Hamiltonian satisfies the property that if I flip all the spins back, so s and minus s have the same probability, because if the Hamiltonian is the same, the probability is also the same. So if I look at expectation value of s, it is a s times probability of each configuration, but for every s there is a minus s also with equal probability. So s minus s becomes 0. So if this is true, the expectation value of s must always be 0. But we can ask, there is a magnet that exists. So how does a magnet come when this symmetry already exists? Okay. So that is one question that comes in phase transition. Another example is a crystal. So if I take these molecules and reduce the temperature to very low value, they will form a crystal. But now the molecules are running around, there is translational symmetry, but a crystal loses I cannot translate by little bit and get the crystal back. I have to move by exactly the lattice spacing to get the crystal back. But crystals do exist, solids exist, so that also breaks the symmetry, which is there in the original Hamiltonian. Okay. Now, so the first thing when you get a Hamiltonian or energy is to look at limits which you can understand well, not just Ising. Any model you get, you ask is there any limit I can try to understand well. So let us try to understand the limits for an Ising model. So one of the statements for the people who are not in physics, there is some quantity called free energy. Okay, free energy happens to be energy of the system minus temperature times entropy of the system. Now it turns out that in equilibrium, when you are in a system like Ising model connected to a temperature bar, fixed temperature system, the configuration that the system takes is the one that minimizes free energy. So this statement you have to take for granted. This is from thermodynamics. It says that the equilibrium configuration is one that minimizes free energy, and free energy is something E minus Ts, E being the energy of the system, temperature and entropy. Okay, take this, if you are not familiar, take this as a statement of truth. Now you can look at two limits. One is when temperature is 0. When temperature is 0, your free energy is just the energy. There is no entropic configuration, and you ask which is the configuration that minimizes energy. That we agreed, if J is positive, all the spins must either be up or they must all be down. So if I look at the mod of magnetization must be 1, because magnetization is plus 1 here. Magnetization is the sum of the spins, it is plus 1 here, it is minus 1 here. Okay. Now, the other limit is high temperature, when temperature is infinity. When temperature is infinity, this term is dominant, this term I can drop. I can ask how is entropy maximized. Entropy is like asking how many configurations are possible. So, I can maximize the configuration by assigning each spin randomly. So, each spin can be up or down, and if each spin is up or down, your magnetization is 0. Okay. In the limit?
Like too many spins.
Oh, yeah. Oh, we are always considering very large spins. The thermo, so
Half of it will be negative, half of this. Half configuration with half probability negative.
no, this is just each spin independent of the others flip up and down.
So what I was saying that each is up and down, and we are assigning randomly with probability half.
Yeah.
So in the large limit you would get 0.
No, I am saying the entropy is maximized. You can ask how is entropy maximized is the question. So, entropy happens to be logarithm of number of configurations. Now, you can ask, I am going to now, so what is my question I am going to ask? The question I am going to ask is, if I give you this configuration, for what magnetization is the number of configuration maximized? So, if I do each spin up and down, there are 2 to the power n configurations, and that on an with a constraint that exactly half must be this and half must be down, that corresponds to m equal to 0. So, if you do this calculation, it is maximized at that point. Okay. It is like a random walk, it is plus and minus going. You ask where is the probability maximized? It is maximized at the origin, which is m equal to 0. So, that is the argument there. Okay. So, now in the temperature axis, we have analyzed this limit, we have analyzed this limit. Okay. At this limit, we know there is no net magnetization. In this t equal to 0, we know there is magnetization. So, there must be some temperature in between, where there is a transition from this phase to this phase. That is the argument. But you can ask whether this temperature is 0 or some non-zero value. If it is non-zero value, then it is nice. If it is 0, then it is not so interesting. Is the critical temperature non-zero or not? Is not obvious. Maybe it could be infinity also. Now, this argument, so there is some rigorous argument which says that only in 2 dimensions and more, Tc is not 0. Okay, so, there is an argument for that. That argument you can look up, or but just take that there is an argument like that. Okay. So, knowing these 2 limits with this argument, it says that there exists a transition in the Ising model from what I call ferromagnetic, where magnetization is not 0, to paramagnet, where magnetization is 0. Okay.
Is that m equals 0 constraint, or is it something like
M equal to 0, I just said that at high temperature, I ask which is the magnetization for which entropy is maximized, and that is m equal to 0. That is the this. Okay. So, when you are given any other Hamiltonian, it always is useful to look at high temperature, low temperature, and some intermediate limits, and from there try to guess what could be the phase diagram be. That is one. But sometimes you are not able to guess. Sometimes only when you do some simulations, you suddenly realize, oh, there was something else. In fact, there are models where these 2 limits are the same, but there are multiple phase transitions in between. So, but it gives you a hint of what to expect. Okay. Huh?
What was D?
D. Sorry, sometimes D is the D is the dimension. So, these models can be defined in 1 dimension, 2 dimension. I define on a square lattice, but you can define in any dimension, 3 dimension, and so on. So, in 1 dimension, if I look at the model, there happens to be no transition. But in 2 and higher dimensions, for a spin system with nearest neighbor interaction, there is. In fact, 1 dimension, there are no models with phase transition, short range interaction. So, that is a equilibrium. D is the dimension. So now, is it okay? Things are more or less. So now we are going to take this Ising model and ask, how can I do some calculation and quantitatively get the phase diagram in some manner? So there is a there are some. So the simplest way to analyze is something called mean field approximation. So don't work with everything correct. You make some approximations here and there, which seems reasonable, and ask whether the answer you get matches with what you the phenomenology. Okay. So so the simplest mean field theory is something called the Curie-Weiss mean field theory, which is what I'll call age old, because that is the one that is there in all the books. So what is the idea? Idea is you take one of the particles and isolate it from its environment. It could be spin here. I could have done for the binary gas also. I could have taken a more complicated system. Then I look at the Hamiltonian and ask what are the terms that involve this particular spin. So, so if you remember, you had a h times Si plus j times Si times the nearest neighbor's sum. Then there are other terms which do not involve Si, the spin Si. These are the only terms in the Hamiltonian that come in the, and here Sj are spin variable, they are fluctuating, they could take any value. Now the idea is, suppose I take this particular expression and I replace this fluctuating spins with its average value. Okay. So I take the sum over j and I say this is on an average same as the mean value. Each spin I replace by the mean spin. Okay. So it is that is why the mean field, I replace the field coming from this fluctuating spins by the mean field of these fluctuating spins. So now since each of those mean value I am calling as m, which is the mean magnetization, q is the number of neighbors of a particular spin, the coordination number. So I get qm. So that is, once I do this approximation, I get a new Hamiltonian which says my new Hamiltonian is, for each spin I do the same. Then my new Hamiltonian becomes minus jqm, which is coming from, there is a j here, j times sum over Si, q come m from here, there is a magnetic field and sum over Si. So now the cross term that came Si Sj, which was difficult probably to handle, has been removed by this approximation.
We know all the SIs and
No, SIs are variables which are still plus or minus 1. Its neighbors I am replacing with not plus or minus 1, but the mean field. That is the point. Okay. So now the Hamiltonian went from terms involving cross terms to just single spin, non-interacting spins. So, so non-interacting problems you can solve. So that is the idea. So the idea of the Curie-Weiss mean field theory is to reduce your Hamiltonian from an interacting Hamiltonian to non-interacting Hamiltonian. But you have rewritten the Hamiltonian in terms of some observable. So whether this procedure is right or wrong, you can only tell from the doing the calculation and seeing whether it makes any sense. The approximation is very ad hoc. Okay, very ad hoc. Okay. So now, but once you have got a new Hamiltonian, so this is, so I have replaced the H Ising with H Ising mean field, which is H effective times sum over Si.
but the H effective term has the interaction parameter.
Yeah, the H effective has not only the interaction parameter, it also has the mean value of the observable, which we are going to calculate. It is some variable, but we normally in your Hamiltonian you cannot have an observable you are going to calculate, but it is already there. Q is a coordination number. For a square lattice is 4, cubic lattice 6, linear lattice 2. Oh, for each particle how many neighbors are there? Okay. So, so this particular approximation again is not alone for Ising model. I could have taken some other Hamiltonian and thought of a similar way of breaking up interaction into non-interaction. It only depends on how we want to do it. There is no the mean field approximation. You can choose an approximation which is suitable for your and see whether you get the answer you want. That is the point. Okay. But once you rewrite the Hamiltonian, then the calculation becomes very simple. So, partition function. Okay. So the partition function is the sum over all possible configuration, with each configuration given by its weight e to the power minus beta e. Okay, I forgot. So, yeah, how much to assume is, but I think this is something that is common to physicists at least, partition function. So, the partition function is sum over all possible spins e to the power beta times the Hamiltonian. The Hamiltonian is H effective times summation Si, which is S1 plus S2 plus Sn. That is what I have done here. But now, each of these sums over the spins are independent. I can do them independently. So, for example, if I do the sum over S1, when S1 is 1, I get e to the power beta H effective. When it is minus 1, I get e to the minus beta H effective. Then there are n such spins. So, I will take to the power n. But this is 2 cos hyperbolic beta H effective to the power n. Okay, so, that is my partition function. Now, suppose I want to compute what is my magnetization. So, magnetization is sum over Si. So, if I take a derivative of this partition function with respect to H, what gets pulled down? It is this into S1 plus S2 plus Sn, which is my magnetization if I divide by Z. So, therefore, if I take a derivative of log Z, I do get magnetization, and this calculation I can just do trivially, and you get that the magnetization is a function of tan hyperbolic beta H effective. Okay. This is a calculation that is quite simple to do.
So there you broke down the partition function calculation.
So because there are two kinds of spins.
Yeah, the spin can be up or down, but the calculation for S1 does not depend on S2. So, I can do it for S1 and take to the power n. The contribution from S2 is the same, S3 is the same. So, I can just take to the power n. Okay. So, the point is that once you have a non-interacting spin problem, you can compute the magnetization in terms of this H effective, but the H effective itself depends on m, because the H effective was H plus JQM from our previous calculation. H effective was H plus JQM. Then you have an equation saying that your magnetization depends on H effective, but H effective depends on magnetization. So, therefore, you get an equation like this. So, now you have an equation for M, some self consistent equation for M, which you have to solve. That equation is not, you cannot write down a solution, but you can ask in geometrically, can you find a solution or not? Okay. So, so let me re-emphasize. So, I am doing it explicitly for Ising, but similar strategies will work for other models also. Okay. So, first let us do for H equal to 0. So, I take the external magnetic field to be 0, then my equation becomes something like this, and I want to ask, is there any m for which this equation is satisfied? Okay. Clearly, if I put m equal to 0, it will satisfy, because right hand side is 0, tan hyperbolic 0 is 0, left hand side is 0. So, 0 is always a solution, but the geometric way of finding the solution is to plot the left hand side and right hand side. So, left hand side is m, which is this green line, right hand side is tan hyperbolic beta JQM, that depending on the value of beta JQ, it can look differently. If beta was extremely large, then the curve looks like blue. If the beta was very small, then the curve looks like J, meaning there is a wide length over which it varies. As you increase beta, the length over which this variation occurs becomes smaller and smaller and smaller. Okay. So, the curves look like this. If it is like red, it intersects the green only at 0. If it is blue, it intersects the green at 3 places, here, here and here. Okay. So, I can have 3 solutions or 1 solution depending on the value of this beta j q. Okay. That is the point of this diagram. So, first question to ask is, if only m equal to 0 exists, that is only solution, there is no magnetization. So, immediately the question comes, when does m star not equal to 0 exist? What is the value of, the only parameter here is beta j q. What are the values of beta j q for which a non-zero m star exists? Okay. Is it okay roughly? No. Okay. I think I'm going on, but if something is not, if you're losing the actually losing me, then I think it's time one should stop. There's no hurry.
So what exactly are we looking for here?
So we are going to ask. So we have found a solution for m. So we are now going to ask. Remember our original question was, do we have a ferromagnet to paramagnetic transition? So do we have, so m equal to 0 is the paramagnet. So now we are going to ask, can we have solution which is m not equal to 0, which corresponds to the ferromagnetic. So now from the diagrammatic thing, you can see there is a possibility of non-zero m star, but not for all values of temperature, temperature meaning beta. So now you are going to ask, what is the criteria for which there is a non-zero value of m star. So then we can construct a phase diagram based on that. So let me continue with this equation. So we are going to ask from this equation, when does m star not equal to 0 exist? Now that is quite easy to see. All that, so you have to just examine the region near 0. So this particular green line has a slope 1. Now if the red line has slope less than 1, there is only one solution. If the red line has slope more than 1, it will become like the blue line and there will be 3 solutions. Okay. So all that one has to do is check what is the slope at m equal to 0. Is it more than 1, less than 1, or equal to 1 will be the transition point. Okay. So I take tan hyperbolic and find the slope. When I differentiate with respect to m, it is sec hyperbolic beta j q m into some beta j q, and I set it equal to 1. That will be the condition for 3 solutions to exist. Now secant square at m equal to at 0 is 1. So I can drop this one. Beta is 1 by kT, which is our definition, and then you get a condition that critical temperature is jq. Okay, that is the condition that comes from there. When temperature is less than critical temperature, there are 3 solutions. When it is greater than critical temperature, there is only one solution, which is summarized in this plot. There is a Tc here, m equal to 0 here, m not equal. There is a possibility of m not equal to 0 this side. Here there is no possibility. So that is the point. For t greater than equal to Tc, only one solution. For t less than Tc, there are 3 solutions. Do we choose 0, m star or minus m star? How do we choose which is the correct solution? Okay. 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 So, but there must be some rule for choosing. If there are multiple solutions, what is the rule? So again I am trying to tell. So when you do this mean field theory for many other problems also, there will be multiple solutions that come. Then you have to ask, how do I know which is the correct solution? Like in nonlinear dynamics, when you do, sometimes you say stability, but stability is no thermodynamic condition. So the condition is not stability, but we can always go back to minimization of free energy. What is the solution that minimizes free energy? And when you do more complicated systems, sometimes the stable system solution is not the one that minimizes free energy. Sometimes the unstable solution is the one that minimizes free energy. So you have to be careful that you should remove this notion from what you learn from nonlinear dynamics and ask, what is the solution that always minimizes free energy? So, here now there are three solutions. Free energy is minus kT log z, but we know z explicitly from our calculation before. So, now forget. So, if I plot this particular function at m equal to 0, cos hyperbolic is 1. So, log 2 minus kT log 2. So, if I plot f as a function of m, it is 0 here. At 0 it is minus log 2. If I go to m equal to infinity, this quantity goes to infinity. So, it is minus infinity. So, it goes down here, it goes down here. So, the curve looks like this. I have just taken the derivative here to show that this is actually true for all m. So, the free energy as a function of m looks like this. Now, so therefore, any m star not equal to 0 will have lower free energy. So, if I have a solution 0 m star minus m star, the lower free energy is the one which is m star not equal to 0. Okay. So, when multiple solutions come for the Ising model, you have to choose the one which is non-zero magnetization. Okay. So, that is what. So, for t greater than T c, we just argued there is no magnetization. T equal to T c, there is only one root, m star is also 0. For t less than T c, there is m equal to m star not equal to 0. So, if I were to plot the magnetization as a function of temperature, it is 0, 0, 0 up to T c, then it becomes non-zero like this. The curve looks like that. Okay. So, this simple model with some crude variables plus minus 1 and even a cruder analysis gave us the ferromagnetic paramagnetic transition. Okay. So, that is that is the point. So, there are some good points there and some bad points there that I will discuss later. Now, the curve looks like this. It starts at 1, decreases to 0 at T c and then goes to T. Is it okay?
So when we derive this Tc is equal to theta jq,
Can we get that Powell's argument from this mean field theory? For we need t greater than 2 for
No, because if I clearly, so if I were, so you said T c is beta j q, no? So, if I put q equal to 2, which is the 1D answer, there is a non-zero T c. So, clearly it does not get it right. It contradicts the what I said earlier. So, mean field theory was not correct. Yeah. So, unfortunately that is true. But if I do a bit more improved mean field theory, that will get automatically fixed. But in this level, you are right. It predicts a transition in one dimension, which is not true. Okay.
Can you go back to the
no,
Okay. Now, suppose I give you a curve which is non-zero up to a certain point and 0 elsewhere, like this one. Now, there is some resultant complex numbers in the saying that you cannot have, if a function is analytic in a region or function is 0 in a region, it has to be 0 everywhere if a function is analytic. Okay, let me rephrase the statement. If an analytic function is 0 in a region, it has to be 0 everywhere. There is some result like that. Are you familiar with that? So, it is not possible to describe this function using an analytic function, because it is 0 in this entire region. So, for example, so therefore, it must be non-analytic at t equal to T c. So, what does non-analytic mean? It means that I cannot do a usual Taylor expansion about that point. I need some other variable. So, if for example, if I derive, ask, so usually if I do a Taylor expansion about a point anywhere, I ask how does magnetization change if I change temperature slightly? It will change by the same, it is m at that point plus derivative times the variation. So, it is always epsilon, the small variation creates a small variation. But if it is non-analytic, that is not true. So, you need to have some other way of describing them. Okay, sorry. So, now let me describe a little bit already I think I have lost a lot of you. So, I will just do one slide to clarify what I meant by the Taylor expansion is not possible. So, I want to understand the behavior close to TC. Okay. So, so to do that, I ask what is the answer if I just sit at a point below TC. So, I will ask say my temperature is slightly below TC. Then I ask from my self consistent equation for m star, I ask what is the value of m star. So, it is a simple calculation in which you have to expand tan hyperbolic x to second order or third order in x. But that calculation if you do, I will not go through the algebra because the net result is that you get if I so when I am at TC m star is 0. If I move slightly away from TC by epsilon, m star increases as root epsilon. Okay. This is just a calculation of this kind. Now, if I had done Taylor expansion, I would have got m star proportional to epsilon, but this is root epsilon. So, this non-analytic behavior is captured by something called critical exponent, which says that in general your magnetization should increase as epsilon to the power beta. This beta is not 1 by t, it is some critical exponent beta. In the mean field analysis, because of this calculation, beta is half. I ran through a little bit.
So how did you get the root epsilon? Like
That is just, I sat at temperature just below critical temperature. Then I looked at the self consistent equation.
Isn't that just for Taylor expansion?
That is allowed.
Yeah, and
Tan hyperbolic is an analytic function. I can expand as I wish, but when I solve it finally, I find that m star has some non-analytic behavior.
okay, so how will you but obviously that if you expanded Taylor then
M star as a function of temperature is non-analytic. Tan h as a function of any variable is analytic. The solution you get is non-analytic. That is all. So this non-analytic behavior near the phase transition is captured by this exponent half and so on. Okay, so let me now, because it is becoming messier, that messy part is not important. So what can be taken away without understanding the mess? So there is a phase transition. That phase transition is accompanied by non-analytic behavior. All phase transitions are accompanied by non-analytic behavior, whether of this kind or another kind. Sometimes how to capture them? They are captured by something called critical exponents. Now, what is the importance of the critical exponents? I will just tell in the previous slide. Now, you can compute them in multiple ways, numerically, calculation wise, mean field theory. They may match or they may not match. So, here there is a mean field theory answer. Okay. So, this is what to take away. Now, I will not. So, similarly you can define other, do not have to worry about the detail, other exponents. For example, if I look at susceptibility, that is how does magnetization change with magnetic field, that goes to infinity at TC. If I look at some other quantities, I get some other exponents. So, there are multiple exponents to characterize the critical behavior. Let us forget about what these details are. But let me summarize what I, so we started with the Ising model, where is the what we call the minimal model of for interaction, the minimal number of variables, 2 variables, minimal interaction. That also we found it difficult to solve. So, we said let us solve it by mean field theory. By making some approximation, we made it from an interacting problem to a non-interacting problem. Then we solved it, but we could get back the phase diagram which I had put in the beginning. So, if we analyze for h equal to 0, we found a ferromagnetic phase up to Tc and then a paramagnetic phase. Tc was Jq, that happened to be in the calculation. Then we could actually, which I did not explain, all the different thermodynamic quantities you can compute within mean field theory. magnetization looks like this. There is a non-analytic behavior here. The behavior around that point can be characterized by some critical exponents. Susceptibility diverges. There is some exponent for that, and then specific heat and so on. Okay. So, now let me spend some time telling some words about minimal models. What are the uses of minimal models and what are the uses of mean field theory? So, water and magnet, the phase diagrams we saw in the beginning, are very complicated objects, but we then analyze a very simple interacting spin model, which I will call as minimal model. Okay. When we analyze those models, we found the correct phases. I did not discuss the liquid gas, but we realized they are the same. For the ferromagnetic paramagnetic, it gave the correct phases. It gave the qualitative phase diagram right. When I say qualitative, it did not give the correct critical temperature, but it predicted there is a critical temperature. Now, what about and it gave some values for critical exponents. What about critical exponents? That I will discuss in the next slide. Okay. Then there was a mean field theory. Mean field theory advantage was calculation was very simple, but it gave a very good intuitive idea of what the system behaves like. It gave some values of critical exponents, but they happen to be wrong. For example, beta mean field was half, but in reality is 1/8. Okay. So, it gave it wrong.
So when we say in reality, are those the analytic solutions?
This is an analytic solution, but you can do an experiment also. You can do an experiment in a magnet or a liquid gas and ask what is beta in 3 dimension and ask what is Ising, and it is not the same as mean field.
So when you say qualitative phase diagram, that means the numbers are not same, but the shape is.
Usually the shapes are got correctly, but the phases are often got correctly. What are the possible phases in the system comes out correctly, and roughly the phase diagram, the if it goes to the right, it normally gets it right. But you have to supplement it with some simulations to show that they are matching. But in your mind, you can have something to fix in your mind. That is the point.
So this is critical exponent only one side.
No, both. For the order for magnetization, one sided, but for susceptibility, both sided.
But like if it is both sided, it would be continuous.
No, continuous as in?
I think there wouldn't be a phase transition.
No, the critical I didn't understand the question. Can you tell the question?
So like critical exponent is like how on what power the error is proportional to.
Yes. So, for example, here I can define this critical exponent only for t less than Tc.
Yeah.
But for susceptibility, I can define on both sides. For this quantity, I didn't explain. So, for specific heat, you can define on both sides. But I'm saying if we know, we can define on both sides.
But would it be different or the same?
Yeah, so there is some result which says that it should be the same on both sides. Okay. Now, so there were some critical exponents we computed. Suppose we did some mean field theory calculation to compute. Suppose I could do the calculation exactly. Then the claim is that if I know the answer for Ising model, it would match the value observed in the experiments. That is the claim. Okay. So, if I were to get the answer in 3D is 0.356, and if I do an experiment, I should get exactly 3.356. Now, this particular way of modeling, where we make the model simpler and simpler, is different from usual modeling of, let us say, I want to model birds flying around. I can make a simple model, but then if I want to understand the bird can take zigzag movement, I have to make more complicated models for better results. Usually that is the case. I make a simple model to understand, then I add details, more interactions to get the answer. But for this critical exponents, you can make it as simple as you want, but not too simple, and the results will not improve by making more complicated interactions. So, if I take Ising model and I say I put next nearest neighbor, that is not going to change the exponents. It will only make the calculation more complicated. So, the answer you get from these simple models is not an approximation to the real answer. It is the model is an approximation, but the answer is exact, which is not the case otherwise, where you have an approximate model, you get approximate results. Okay. So, why is that the case? So, there is something called universality, which is says that these critical exponents are not sensitive to the model you do. So, this particular aspect, so suppose you were trying to model some complicated social behavior or something, and you find some exponent numerically, then you find that that exponent is close to something that people have studied before, a very different model people have studied before, then it is quite possible that these two models belong to the same universality class. So, one can try to make the claim that the exponents here are the same as that universality class. So, I can read the answers and solutions from those models, which are much more simpler than what you have studied. Okay. So, the Ising model, in fact, what you see in the Ising model answer is the same as what you see if I take carbon dioxide and go from liquid to solid. It is quite remarkable that the answer is, for a very different system, it is exactly the same answer. Okay.
And the exponent is the same.
Exponent is the same. So therefore, this has triggered in StatMech a study of minimal models, where you do not get everything about the system, right? Many things you get exact. Okay. So, there is a lot of understanding also you get, and quantitative answers also you get exact. Okay. So, now, but of course, the analysis, mean field analysis does not do full justice.
So minimal model, if you have a model, you somehow reduce it to minimal model.
Minimal model is your choice, but if you make it too simple, suppose I take Ising model, but do not put the J interaction and only have HSI, then it will not capture the interaction.
So any complicated model you can reduce, like make it to some minimal model, and you do this type.
Yeah, but if you do if you don't, if you make it any simple model you wish, it may not capture the system you are modeling. So, that is what. So, the minimal aspects in the end depends on what symmetries you have in the problem being modeled, that those symmetries must be present in the system minimal model you make, that is the claim. So, that you have to make a judgment in that. Okay. So, the analysis was a mean field analysis. It has lot of drawbacks. It has advantages where it gave you intuition, it gave you phases, it gave you qualitative phase diagram, but it has many drawbacks. One is an ad hoc approximation. The Hamiltonian itself you changed in some arbitrary fashion. Then now it depends on the observable itself. Now you do the analysis, you have no idea whether that Hamiltonian is going to give the same answer as the original Hamiltonian. In this case it gives, but it is uncontrolled and not done systematically. Then it, as somebody pointed out, it predicts phase transition for one dimension, which is not true. Some other thing which I did not show. So, there are many questions from today's classes which even if you have not followed, is there a better way of doing mean field theory? Then the answers were not quantitatively right. So, how do you do simulations for any of these, not just Ising, but if you are given a model, how do you do simulations? Sometimes it can be a system in equilibrium like Ising, sometimes it can be a system out of equilibrium, which is different. And what are other well studied spin systems? So, since I feel that this part is quite important in modern world, I will try to do how to do simulations first, then I will try to discuss, if I have time, I will have time, what are the other common well studied spin systems. Then if I have time, I will do better way of doing mean field theory. So, the next class will be unconnected to this class. So, even if you have not followed, I will try to make it general for how to do simulations for interacting particle systems. I will try to Monte Carlo simulations. So, I will stop here. I took some time extra. Is there Shakti's class thing now? What? I am sorry, I took some. Any questions? Yes.
How can we relate what we studied to biology?
So that part, how do you relate to biology? So this one will come later. So for example, the spin system, you can even think in terms of decision. What is the word called that? How do voters affect each other? You can think of them as people and each one has an opinion, and it can affect the opinion of the nearest neighbor, and then you can make some dynamics like that, and that gives you some way of how opinions propagate in time. Now, whether such models are realistic or not, you have to make a judgment depending on what you see and what you model. So, that part will be discussed. Opinion making and decision making, I think spin systems for them will come in later specific contexts.
So this idea of spin system is like abstract, which can be extended to
So,
bio.
so this spin system is just something with two variables, something that can have two variables and interacting. I have discussed in the context of phase transition, but you can discuss it in the context of some other. You can make it three opinions, or I don't know. You can make it in the context of any other sociological problem you are modeling.
I mean, specifically in the context of hierarchy, your next nearest neighbor to your right is actually shown that you can take the cell-fate choice problem in developmental pattern formation, where a cell decides whether to become, let's say, epithelial cell or a skeletal cell. So you can take the complicated biological model and you can actually reduce it to the easy model, where the two states corresponding to cell-fate choice E and cell-fate choice B.
No, the interpretation can be many interpretations you can analyze, but it need not be exactly Ising. No, you can take a, sometimes you might have that I affect my nearest neighbor in one way, but next nearest neighbor in another way. So I can make rules as I wish, and you will get different phase diagram. And sometimes, if you are, it depends on your intuition. If the modeling is right, you get the behavior right.
So for more details, you ask your next nearest neighbor to your right.
Yeah. So that is.
I just had a question.
Yeah.
Generally, we think of when we define energy, we just assume that the system is trying to minimize the energy. Right? So, but you introduce free energy in one of the guidelines.
Yeah.
Right? So, can you just
So normally you minimize. Normally don't minimize energy. So in fact, there is this standard example. I can not standard example. Suppose I take a marble in a egg carton and I put it in oscillation. Where will it come to? Will it come to rest? In the bottom. Why? What is the criteria for coming to rest at the bottom? Energy dissipation. Energy, is it energy minimized? Is there some, what did you say? Energy minimization?
Stable equilibrium. If you move it
Lowest potential energy. Somebody said lowest potential energy. But
the direction of the radiation.
so you just come to lowest energy position, let us say. Kinetic energy is also zero, potential energy is also zero. But total energy is conserved, no, in the universe. So if I take the total energy of the system, then the environment energy has gone up. So if I apply this principle of minimum energy to the environment, clearly that is maximized. So there cannot be a minimum energy principle. So what is minimized there? What is minimized is something else. That minimization is free energy. It says that it's not just energy, but how the energy can be stored. That is the entropy part. How many ways can I store energy? So therefore, this E minus Ts comes, where S is like how many ways can I do things. So if I can do things in many more ways, it lowers free energy. So then I minimize free energy. So the marble comes to rest in the bottom of that thing because energy can be stored in multiple ways in the remaining universe. So therefore, the free energy is minimized.
So how it scales up, there is no proper symmetry and the states are there.
Sorry?
If there are like more states
Yeah.
and there is like less symmetry. Or
Yeah. So in the thing about other popular spin models, in the last lecture, I will discuss spin systems with 3, 4, Q state, so the symmetry will change. What are the possible ordered states? What are the kind of phase transitions you see? I'll summarize without going through the calculations. Because the symmetry now it is plus minus, there is a, you reflect, but then it becomes a permutation, some other symmetry it becomes. We'll discuss that.